just as an overview for everyone that's here, we've got 3 speakers of demos of data sets that are cloud native. So just trying to show the benefits of cloud native data, and maybe you have a data set that's not cloud native that you see this example and it inspires you to convert it to a cloud native format and use all the amazing tooling that exists for cloud native geo. So with that, I'll pass it off to Max from Fused to kick it off.
All right, so I'm going to share my screen. Can you see the screen?
Yep. Yeah.
Okay, cool. All right, so I'm a dev advocate at Fused, and we basically want to make it a lot easier to iterate as a data scientist and to deploy stuff a lot easier. We want to make the whole like complicated deploy thing a lot easier. And so I probably don't need to convince a lot of people here that there's a lot of cool data that we're putting more and more in cloud native formats. It's really cool. You can tile it, you can chunk it, you can work with huge data sets. So the data set part is like, there's a lot of really cool stuff. The problem is when then I'm a dev, I'm in VS Code locally, there's a bit of a disconnect sometimes between like being able to work with that. And so that's where we want to sort of try to come in and make that a lot easier. So I'm going to take the example of the Overture maps building data set. I'm guessing most people here are probably familiar with that, but in case you're not, Overture is sort of a agglomerate of a few companies to put out data sets out there. And one of those data sets is building footprints. We've repartitioned some of them here, but basically it's building footprints with some info about all buildings for nearly anywhere in the world. So we've already started working with Overture to make it accessible through Fused. And I want to show a little bit of what that means. It's not just like, great, there's another tool, yet another tool out there. So I'm going to attempt to do a live demo here of what this looks like. So this is Workbench. This is our browser-based IDE. And it's built around this notion of UDFs. So you can see it's right here. And UDFs are what we call user-defined functions. So they're Python functions with a fancy wrapper on top of them. What that means is now this function is deployed just by adding this decorator on top, and you can call it from an HTTP endpoint. So I can call, I would get a link and I can call this and I would return a geodata frame. Now, why do we have a browser here? You don't need to use it, but the really cool thing about it is now I have basically Overture that's rendered and pulled in real time in my viewport right here. So I can start to do some fancy stuff like print my data frame. And so it's going to show up in here if it wants to work. I can also do, it's not doing it, which of course is always what happens. Whoop. This is what happens when you want to do a live demo. What I can also do is basically query it. So if I have this data set right here, just want to show that this is basically Overture data. You can see that we have all the property. It's coming from OpenStreetMap. There's all these things. I'm going to just refresh this page. I'm sorry, I'm in internet connection. It's not very good. This is what I get for trying to do a live demo. It's not going to work when I want to show it to you. So I'm going to talk about these UDFs instead. I'm sorry that this doesn't work. Basically, what should happen here is that if my connection was a little bit more stable, we would be able to, as I parse, for example, just buildings above a certain area, all the smaller buildings would disappear. And then I can just return these data frames. Then in here, we can pass different parameters and get a HTTP endpoint that I can like wget or curl, and I would just return a GeoJSON. And so if I come in here and I remove this, now I would get all of my buildings. If I would add a head 10, I would only get 10 buildings back. And so I'm not deploying anything. I'm not installing anything. It's just this code is right here. the demo's not working. But basically, that's what we're doing. I'll share some links to Fused itself, to some of the documentations in the Overture maps, and to Source Cooperative. This is pretty cool.
Awesome. Yeah, no worries with the live demo. That's just how Murphy's Law goes. But send
Yeah,
some
that's what
links
I
and
get
people
for
can
it.
find. Yeah. No, it's fine. People can it got a good intro. I can go play with it on their own later. So yeah, just shop some links and then we'll pass it off to Cam.
Thanks, Michelle. Yeah, I want to use Fuse for the work that I'm doing now. For those that haven't met, I'm Cameron. I'm the Director of Digital Technologies at Bridges to Prosperity. And at Bridges to Prosperity, what we do is we address rural poverty by building physical trail bridges. These are bridges that connect people that are walking to critical infrastructure, like the bridges you see here on this page. Move this here. And one of the big problems we have, or one of the big problems we have when trying to scale this intervention in rural areas, is figuring out where these trail bridges are needed. And that's one of my main jobs in the digital technology division here at Bridges to Prosperity is, can we figure out where bridges are needed at scale around the world and figure out what their impact would be? And can we do that using remote sensing data so that we can make better use of our people's time that are on the ground in those countries? The problem with this is that many of the bridges we've built in the past are on unmapped waterways. There are huge data gaps in rural areas, and those are the areas we work. And so we set to work trying to build a novel machine learning model that would find rivers and waterways around the world better than the current technology. And that's what I want to share today. We're sharing it on Source Co-op. I published it last night, so go check it out. The model is called WaterNet. It's a new global data set, so we work mainly in East Africa right now, but we built this model and deployed it around the world. And we tripled the extent of found waterways over hydrosheds and then TDX Hydro, which is the machine learning add-on to hydrosheds. The waterways we found more than tripled the extent of those found in those data sets. You can see here, this is an example, I think, in Ethiopia. The blue is what's currently found in current data sets. The green are the additional waterways we've found. Here's an example from Kenya. These waterways, again, blue are what's been found in the past. Green are what we found in addition to those. We also have small applets here where you can explore this for yourself. Here's the raster data available on Source Co-op. The darker blue something is here, and visualization is the more confident we are it's a waterway. And you can see this data is global. It's really beautiful. Just you can really see the world is alive. And you can explore these waterways in raster format around the world. We also are launching a small vector app as well. So again, here's the green are the ones that we found in addition to current models. And the blues are the ones that have been found already. And you can access the data in GeoTIFF format, Parquet, or I've also uploaded PM tiles if you want to use these in maps. So it's all available in Source Co-op. And I just launched today. We'll have the machine learning papers coming out on this later this week and later this month. But we're really excited for people to use this. We're already seeing researchers use this for a variety of applications. We're going to use this in our work. It'll act as a magnifying glass to help us find where these bridges are needed. If you do use this or you want to use it or have any questions, please reach out. I'd love to hear how the world is using this data. And then if you have any feedback, let us know.
Very cool. That was awesome. And yeah, the link for that is about to be in the chat, but it's also in the description of this talk. So if you want to check that out more, it's on Source Co-op. Cool. And then we'll just pass it off to Carl for the last demo.
All right. So thanks, everybody. That was amazing. For lack of better wisdom, I'm also going to try a live demo. I'm going to be talking about a data set that is already available on public data, the GBIF, the Geospatial Biodiversity Information Facility. You heard Javier mention just how hard this is to visualize, at least in early formats at the keynote. But what we have done is to take the advantage of having a platform like Source Co-op where anybody can kind of remix or add value to a data set. So all I have done ahead of time is stream that data set through our machine to add H3 spatial indexes to the lat long coordinates in the data so that we can make it easier to visualize. Adding those indexes takes like a day, so it's worth kind of pre-processing for people, and then that's available on Source Co-op. And we're going to see what we can do with that. So here I'm in Jupyter Notebook, load some simple libraries, and I'll be using duckdb to talk to that point data that has those spatial indexes. So I just make a connection and set some credentials. And here we go, we're ready to talk to that data. I just name my bucket on Source Co-op or an S3 location, and it begins to run. So I'm going to start by running through that data and collecting every individual point observation and aggregating them to this H3 level. So I'm tiling the Earth with 41,000 different hexagons. So we're grouping those by hexagons, counting up how many observations of all species in the world, or here I'm just going to say all insects in the world to kind of give a subset, and then putting that back on S3 so that I can render it in a map. Took us about 10 seconds. It actually probably takes us longer to render the map, just because now I need to have DecGL read that in to my computer. Okay, so we have the globe here at this H3. That was fun. Let's try a more ambitious resolution. That was 41,000. Let's try 2 million hexagons. So much bigger calculation. We're going to just, again, stream that across the globe. Every hexagon on the globe, count out how many observations we have at this much finer resolution. Okay, 11 seconds. So much bigger data object, so this may crash and freeze my machine. We'll see. To try to visualize this. So we have processed the data in streaming fashion with duckdb and streamed our resulting hexagons back up to the S3 bucket where we can render it. My browser tab is now reading in that data, and we'll see how slow it is. It says, yes, just that last layer of that JavaScript visualization is going to take a moment, and there it is. We've got the globe at much finer resolution where we can see places where those species observations are very dense and where they're less dense. We can zoom in even more. Let's just give this a go. What if I don't want to do the whole globe, but I just want to zoom into Yosemite National Park? And I can zoom in into particular species. Let's say I'm interested only in bears because we love bears. So here, same idea. I'm reading directly from the remote S3 bucket, but I'm filtering down to that polygon of Yosemite using well-known text. And I'm also grabbing only bears. And we're going to do a much finer spatial resolution because we've zoomed in. So I'm using H9 cells here. Okay, 17 seconds. Let's see. I again post the result as just a GeoJSON file back on the S3 bucket so that it's available to the world, and then try to make some hexagon layer of that map here. And here we go. We've zoomed into Yosemite National Park. And where are the bears? Of course, the bears love the valley. And if we go in and see, their most observations are right in Yosemite Village. All right, so that's what I've got. Thanks. Back to you, Michelle.
Awesome. No, these have been great. There's a question for Carl in the chat. When someone generates new data
yeah,
set-
it's stored for, well, it's just, I'm pushing to Source, so it's stored as long as Source keeps it up there, or I keep it up there. Unless I overwrite that. So when I'm doing a demo, you saw me, I was just writing something called example. So it's a nice temporary thing, and I can like overwrite it as much as possible. But if I want it to persist, it'll persist. Yeah, there's some finesse to make the demo work. So if you're in the local region in AWS, it can run much faster because you have much more bandwidth. If you're bandwidth limited, it'll be slower. So I'm kind of mimicking that compute effect. I am using those formats because DecGL understands them natively. The outputs are small. They're way smaller than like ones I've tiled them into like at H5, or I've subset them. They're much smaller. you know, we went from half a terabyte down to something that's probably like a half a gig.
I saw a question for me in there. It's fun to share this, by the way. We've been working on it for a while. It's also a cry for help. Somebody asked, Kushang asked if it's possible to provide WaterNet as a single PM tiles file. I'm trying. It keeps erroring on me. I figured out that some of my errors are caused by working on an external hard drive, so that was annoying. But yeah, that's the goal. So hopefully, and you might see some chatter in Slack about troubleshooting this with me. So if anybody has ideas or want to offer advice, come find me.
I'll just echo Cameron there that like most of what I shared is like the cloud native community has like taught me like how to do this in the past couple months. So kudos. And if you're not on the Slack, come and ask questions like me and get amazing advice.
Yeah, and yeah, I will echo that as well. Everything that's on Source Co-op was thanks to advice for people on how to format things. And so if you have ideas on how to even make it more accessible, feel free to let me know.
Awesome. I think that's a good stopping spot. If people have more questions later, they can find you either in the meet and greet or at another time. So thank you again to you three, and I'll see everyone in the next session.